Right, so we'll start working on operational amplifiers starting from today. And there's a tutorial due on Friday, I guess. I forgot when the homework is due, maybe next week, like Monday or Wednesday. So I want to show you a schematic first. This is another class I'm teaching here at Mines. If you're in computer science, following the computer engineering track, probably you have to take this class. It's called Embedded Systems. It's a really fun class. I also teach a microcontroller or embedded system class back in Durango. But you know, the professor here, Chris Colston, he is on sabbatical like what I'm here right now. But he developed everything here for the labs. It's a really intense class. However, you are going to learn a lot from hardware level to register level. Highly recommended. So the reason I want to show you this is, if you look at the board, he designed actually has several operational amplifiers on it. So especially for students in non-electrical engineering majors, maybe op-amps are the components that you'll use a lot if you're not an electrical engineer. Other components, I'm not sure. For example, the digital parts like the little CPU, microcontroller for digital signal processing or digital control, okay? You may not have to use this one. However, op-amps is a really common component on the circuit. So if you look at this one, this is basically a microphone amplifier and the filter as well. So it has a little high-pass filter and low-pass filter to get rid of the noise and offset, and then amplify the signal. And also there's a audio amplifier as well. It's a IC chip, so you are not seeing the structure over here on the schematic, but it has several operational amplifiers in it. And this is a low-pass filter. It's also being built on a op-amp as well. So you can see, to process signals, you just have to use op-amps in a lot of cases. It's a really common component you are going to play with. It's not really fun to learn the basics, but it's really fun to build circuits using it. Right? So now let's get into the basics. So make sure you can be successful on tutorial 6. Okay. I'll go through the midterm exam problems probably on Friday, I think. Yeah, Friday. We'll do that review. Okay, so first, the two configurations. RF, R1, so you have to use this in your mind. The fundamental structure of the amplifier configuration here. There are a lot of things going on, a lot of fun stuff to build actually. If you want to build a robot, for example, very simple robot car being controlled by an IR signal pair, IR sensor pair, and most of the cases, if you don't want to get any microcontroller involved, you're just simply using an op-amp to form a comparator. I'm going to show you the schematic really quick. It's a really fun project. For mechanical engineering, sometimes you have to build the robots, right? Let me show you how we can do it. Freshman at First College. I do this experiment in their freshman. It's called first year launch class. In their freshman year, they take a 1 credit class, 3 hours on Monday. Let me show you that really quick. I hope I can see here. Oh, she helped building that. I think that's this guy. All right. So it's a motor driver, and you can see this output is actually from the output of the op-amp as a comparator. I'm going to show you why the comparator is going to do this job very soon. And has two DC motors, and these are the IR pairs receiving a reflection from the table. If it's a white light color like a paper, it's going to reflect the IR light. And if you have a tape in the middle of the table or on the paper on the light color platform, then shows a black track. So the IR sensor emit IR light to the tape. The black tape is going to absorb it without reflecting any light. So it is able to follow that track. So you can make a line tracker using a very simple analog robot. You can build it probably within like 2 sessions of a 3-hour labs. Really fun project. So these are the two IR lights with a little op-amp on it, forming the little comparator circuit. I'm going to show you that today as well. So there's a demonstration here. It's really simple. No computer, no brain, no CPU, right? There's no like intelligent component. It's just a very simple op-amp circuit, and it works. It's a 6-hour work, right? It was realized by that little op-amp comparator. It's powerful, right? You can build amplifiers, you can build comparators, you can build robots by using amplifiers. Very useful stuff. Okay, so this one is called it's a inverting configuration. And there's another structure. Let's keep this one on the top. Still feedback here, or this one goes to ground. So that's two structures, two main structures. This is called non-inverting. If this is given to you, there's no feedback, no negative feedback. And you need to know that the device being designed by whoever, analog circuit engineer. So this op-amp has a feature, it's called open loop gain. Very likely during the interviews they will ask you this kind of question. A lot of instrument design positions with the DoD. It's actually a very big industry in the U.S. If I look at all my students who graduated from First College, get a good job in the instrument design companies, and most of them are DoD contractors. So getting defense contracts, and they are building instruments using amplifiers, using digital systems as well. Okay, so for this one, if they during the interview, like the DoD agents comes over for career fair and ask you, what's the open loop gain of an ideal amplifier like this? It's infinity. Keep that in mind. Very common interview question. It's designed. They won't ask you why. You just need to know it's designed that way. Okay, so open loop gain means it's VL equals VP minus VM times that open loop gain. So A is the gain, OL is open loop. So open loop gain times VP minus VM. Always keep that in mind. It's designed inside the triangle. We are not designing this op-amp. We are using this op-amp. So you need to know. It's like a user manual. You buy a microwave and ship to your house, right? You have to look at the user manual. You don't. Microwave is so easy to operate. Something else, right? You have to look at the user manual and see how this works. Same thing. It's just a user manual. Okay? Treat it that way. Very simple. You buy a new stuff, new appliance to your house. You look at the user manual. So on the first page of the user manual, you'll see this. VL equals VP minus VM, which is the non-inverting terminal minus the inverting terminal, whatever voltage applied to these two terminals, and times the open loop gain to get a VL. Confirmed. Okay? That's on the user manual. And that's the first thing. The second thing on the user manual, it tells you that the open loop gain, which is this guy, is infinity. For ideal op-amps, operational amplifiers. For ideal op-amps, the open loop gain is infinity. Okay, but usually it's just like 1 to 100 million times open loop gain. It's huge. For open loop, keep that in mind. You don't have a feedback, but these ones they have a feedback. It's gonna change. It's gonna change the gain, the voltage gain over here. That could be very confusing. But now let's just know that. Keep that in mind. If you don't have a feedback, here this is a equation to build a relationship between the inputs and outputs, and also the open loop gain is here in the infinity. Okay. All right. So now, because of the infinite open loop gain and the negative feedback, and it's going to give you a feature of the op-amp when you have a closed loop, things starts getting confusing, okay? And that's a very common interview question. So what's that?
What if I put a higher voltage in the inverting current? Then do I get a negative, like in ideal sense?
Yeah, we'll cover that in a bit. Yeah. So if you have higher here, it's going to be a negative voltage depending on your upper and bottom rails. So the rails means it's a power rails. It could be power. It's the power on the top. It's usually like being labeled as VCC. It's a collector with the BGC transistors. This is too much, but let's just remember it's usually labeled as VCC or VDD as a power and GND as a ground. So you build your circuits within the two rails. These are called power rails. Okay, during the interview, just tell whoever interview you, right? So the voltage range has to be within the two power rails. Sounds really professional, right? Has to be within the power rails. If it's over the power rail, not just for the inputs but for the outputs, it's going to saturate. You'll see that term on the homework and tutorial a lot. So it's going to saturate. The reason for that is it's providing, for example, 5 volts. Usually you are seeing 15 volts. Doesn't matter. So plus minus 15 volts from the two power rails. It's just basically just providing a range for the signal to swing. And if your inputs, for example here, let me give you an example, like 1.2 volts, okay? And here's 1.0 volts. What's the difference? 0.2 volts, right? Times this one, what's the result? Huge. What's gonna happen? Are you getting like millions of volts as the output? It's impossible because the power rail is not providing that voltage. What's gonna happen is it's gonna saturate at the maximum. If you're getting VPs bigger than VM, what's the maximum voltage you're getting? Even though there's a tiny change here, a little tiny change, which are having 15 volts. So it's gonna saturate. So if you have VM a little bit bigger than VP, what's gonna happen? It's gonna saturate where? Negative 15 volts. So eventually, for this kind of configuration, 0 is not the lowest voltage you have in the circuit. It's gonna be negative 15 volts. So it's gonna, for example, if this one is varying, this brings out a really good concept over here. Super practical, right? Let's see. The full power rails are, I just label it whatever we have over here to keep it consistent. Okay. So the voltage for VM is 1 volt. For VM. Okay. So let's see. For example, I have a signal, varying signal. For VP, it's changing like this. I'm asking you what the V out looks like. This is VP. Keep that in mind. AOL is huge. Even though there's a little change, little difference, will be amplified by millions of times, will saturate the output immediately. So what that means is, for example, starting from here, VP is lower or higher than VM? Lower than VM, right? Before this point, VP is lower. So what are you supposed to get? What are you expecting? Negative 15 volts. Until here, right? What about after? Whenever it's slightly bigger than VM, what's going to happen? It's going to saturate. And last. So at this point, it's a little bit less than VM. It's going to saturate again. What is this called? It's called comparator. Super important in practical circuit. So if you keep this open loop, it's going to form a comparator. It's using that open loop gain to amplify the differences between the two signals.
So is this basically just turning an analog signal into a digital signal?
Yes.
Okay.
Yeah. So what's going on for the little robot car there? What's happening is I set a reference signal for the two wheels of the robot. Let's just see. Here's a black track, right? And I got two sensors over here, right? And here's a car. The sensors are over here, and these are the four wheels. These are the sensors, okay? What's happening is whenever if the sensor here is out of track, for example, this sensor becomes get on the top of this black tape, the light is getting absorbed, so it's not receiving a reflection. So what's happening is the signal being received here and here will be different. So it's gonna turn off. Which wheel you want to turn off? Question I'm gonna ask you. For example, I'm only driving. It's a front wheel drive. It's not a 4-wheel drive. I'm only driving these two wheels, right? So if it's, for example, the car tilted to that way, which wheel I want to keep it on, which one I want to stop to put it back to track? The left. Wait, it's.
The right wheel.
The right wheel should be off, right? And this one should keep on. So what's happening is whenever it's out of track, you want to stop this one and keep this one rolling. So pulls it back. All right? Because the circuit can do this really quickly, adjustment really quickly, so it's keeping the car on track. That makes sense? Okay? And you are using this pulse whenever it's out of track. Okay? You keep one of them on and turn off the other wheel. So the comparator working super fast because of the huge open loop gain. It's going to respond really quickly whenever there's a little tiny signal change. I'm not drawing the internal circuit over here. It's complicating things. But what I'm telling you is, if you look at the output of the comparator, you'll know that you're turning on all of the motors. Depending on the signal, you are turning on and off. So you can use these signals to control the DC motors of the two wheels. What's that?
So when you have the two like side inputs to it, those are like sort of like a reference voltage for what the maximum is?
Yeah, so you have to set a reference voltage in the middle, usually in the middle.
Okay, and then one of them is like say 15 volts. And the ground is always 0 volts, but it can also output negative 15 volts.
No, so this is usually for these types of circuits, it's trying to make things easier for beginners like you guys. It's first time learning op-amps, so we want to use negative 15 volts as a bottom rail, so we can keep the signal swinging around ground. So we are not, when we are dealing with these kind of circuits, we just ground the non-inverting terminal. If you have a ground here and 15 volts here, you cannot use ground. You have to lift it. It's called DC offside. So we'll talk about that later. Now to make things simple, we just have to do a negative voltage for the bottom rail, so the signal is swinging around ground. That's why we can ground here. We'll get there later.
So it's not okay to ground the non-inverting terminal and put a ground.
If you have ground as the lowest voltage over here, if you ground op-amp, you have to lift this signal by, if it's 5 volts, you have to lift it to 2.5 volts. So the problem is, for this one, right, the lowest rail here is negative 15, right? So your signal is allowed to swing around ground, which is okay because you have room here. I know it's very abstract, but since you have room here, so it's able to swing back, swing lower than ground, because you have your bottom rail to be lower than ground. However, if you ground here instead of have a negative 15, so not negative 15 anymore, right? The lowest voltage is ground, then your signal has to swing around, swing above zero. So I have to provide a DC offset in the middle, so it's going to swing around that DC offset called 2.5 volts, or let's say 7.5, because it's 15 volts. That's how we have to do it. But now, since we have negative 15, so we don't have to worry about the DC offset. It's trying to simplify things for people who, learn this the first time, but actually not very practical. Since usually we don't provide a negative voltage on the board. Its lowest voltage is just ground. We just have a common ground. Starts getting confusing, right? But I believe if I keep repeating those concepts, it will get clear later, all right? So no worries. Now let's just keep in mind that we want to connect this one to negative 15 volts to provide a negative voltage, so it's able to swing lower than zero, okay? This is just one example to show you the open loop conversion.
So in that example,
Yeah.
it's okay to have, it would be okay to have VM equal to 0 volts because our rails
Yes.
go from negative 15 to 15.
Yes.
We just chose one because
Yes. So you can set a VM to be 0 because we have negative 15 here, right? So our VP will swing.
from,
I just move this one to here, right? So
Yeah.
no difference.
okay.
Just follow the same method to find out output. So this is a comparator. It's a super practical circuit. However, don't want to confuse you guys. The tutorial doesn't have any comparator circuit in there. I don't even know if they have anything about comparator in homework 6. It's looks very similar. In the future, it's going to confuse you because if you don't learn this, okay, if you look at the difference, this one doesn't have a feedback, but this one has a feedback. Okay, it's the difference. So you'll see these circuits in the assignments a lot. So now let's come back to these ones and see what's the difference. What the differences are. So let's start with the inverting configuration. We have to finish the main problems in tutorial 6 because it's still Friday. R1, ground. So let's assume this is negative 15 for the bottom rail and 15 for the top rail, and we are grounding the non-inverting terminal. What's that?
I guess I was just wondering if, like, we discussed how the comparator provides, like, if the gain, what sort of loop would I want if I just wanted, like, 2 times gain?
You cannot, because that's a comparator. If you want a 2 times gain, you have to use the feedback. Yeah.
Yeah, so, like, how would I get that with if my motivation is I want to gain 2x on the signal?
Yeah, so it has to be this. You cannot use this. It's a comparator. You have to use feedback to achieve that.
Okay.
And now let's go through that. Okay. So here's one thing you have to know. Last time I told you to remember that, but now let's see if this makes sense. If you know the open loop gain now, right? Based on whatever we learn here, and see if that makes sense. So it has to be, if you want these 2 terminals to be, it's called virtually shorted. That's another concept, okay? Virtually shorted. They are virtually shorted.
Is there any reason why we're grounding the positive terminal rather than the negative terminal? Or is
It's okay. If you don't ground it, it's going to provide a DC offset. So it's adding to this point.
okay?
It's going to lift the signal. So for example here, right? This 15 and negative 15, right? It's going to swing around here, or ground. If you provide a DC voltage here, for example, 2 volts, and the signal is going to swing around 2 instead of 0. But that's not ideal because you do want a signal swing around 0 because you have an even room on top and bottom.
Okay, that makes sense.
So for example, if you have a, if you swing a signal, it's a sound wave, let's say a sound wave. So you can do it like this, right? You can amplify both sides in the same range. If you have the signal swing around this line, when you want to amplify it, definitely you can amplify the bottom part of it, but on the top it's gonna saturate. It won't look like a sine wave anymore. It won't be able to go up like that because your 15 volts is right here. You don't have anything above 15 to provide to the signal. So ideally, keep that in mind. Always set the baseline to swing to be the middle of the range.
Does that say R plus or RT?
RF. It's called feedback. It's a feedback resistor. Okay? VP and VM. Alright? So VP minus VM times AOL equals V out. Alright? What's happening here is, so what if VP becomes slightly larger than VM? What's gonna happen? Because of the open loop, huge open loop gain. If VP is larger than VM, what's gonna happen? You are getting a huge. So what's happening in the circuit is it's trying to have a surge for VL, trying to go up whenever it's getting a little bit larger than it, trying to go up. Whenever this voltage is trying to go up, even just a trend, all right, it's gonna dump current to this point, okay, and lift the voltage over here to make it equal. And that happens really quickly because of the feedback and the huge open loop gain.
So you can just send a little pulse.
It probably won't even happen. It's just like a trend, a surge trying to happen. But because of this is huge, so it's trying to happen, it's gonna adjust it. Then they become equal. They don't have the problem anymore. You know what I mean? So it's a really fast feedback to keep them equal. This brings up another super important and common interview question over here. What's that?
Isn't there going to be voltage drop across the feedback resistor though?
It had voltage drop already, right? But the thing is, let's see how this is making this higher. Because previously you don't have anything over here, right? Because they were equal. So for example, they were equal. What is this? 0. Right? If they are equal, what is this? 0, right? If they are not equal, this is larger, you are getting a positive voltage. So this voltage will be positive, not 0 anymore. And will be positive. Because it was not adding to it, you can think about this using superposition. So this positive voltage will contribute to this voltage and adding to it. You know what I mean? So for example, there are two voltages at the very beginning, right? Let's start from zero, from nothing. So they are equal at the very beginning, okay? Let's start from there. It's taking too much time, but if they were equal, this is 0, right? Because of how this is designed. This minus this is 0 times whatever is still 0, VO is 0. Okay? But you do have VM to be something. It's not 0. The subtraction is 0, but VM is not 0. Okay? So it's VM over there. Whenever this becomes positive, if you use superposition, okay? It's like this is a VM pin, you have VM contributing to it, you have VO contributing to it. So whenever you have VM to it and analyze the contribution of V out, you short VM to ground, then you look at this voltage. If this is positive, it's going to contribute the positive voltage adding to it.
So if you put a feedback resistor, VO is always 0?
VO is not, no. I mean, I'm just saying for this open loop version of it, it becomes 0. But however, since you have all these things, these are getting around this op-amp, so you are eventually getting a VL to be contributed by V in instead of whatever over here. It's also a superposition problem. Let me see if there's a better way to explain that next time. But for the native feedback mechanism over here, you can tell what you can tell is for this part of contribution to V out, what's happening is if this part contributing to V out is this is slightly larger than this, and this becomes there will be a little pulse trying to have a little pulse, but it's feeding back to it and makes them equal. So because of this, it's always making these two equal. That's why if you have a ideal op-amp for this, this is like infinite open loop gain, and the feedback has to be negative feedback. Then the feature of this inverting configuration will give you a virtual short circuit. What does that mean? So these are equal. That's called virtual short. They are not physically shorted. They are virtually shorted. So the conclusion here is, in the interview, if they ask you why the op-amp, the two terminals of the op-amps are virtually shorted, super common question. It takes a while. Don't worry about that. Takes a while to get into it. It's the first time we introduce it. Even for electrical engineers like senior year, they still cannot answer that question for the interview. What's that?
What would be a use for something like this?
Oh, what would they use? Because sometimes you would want to amplify the signal as a comparator. You want to amplify by 3 times, 2 times, 4 times,
Right.
instead of like this digital signal. You don't want to. You don't always want a digital signal, do you? If you are amplifying a audio signal like a song, you want to hear a song, right? You don't want to hear a boom boom. Okay, so it should be a song. Should be a signal, time varying signal. So, if during the clarifiers they ask you why the op-amps, the two terminals of the op-amps are virtually shorted, I'm going to repeat this again and again for this whole semester. Okay, don't worry about that. So you need to answer two items, 2 bullet points. What are they? First, my question here for you: are they equal? Why? Comparator, are they equal? How could they be equal? They are not equal. Like you have VP to be a like time varying signal, but your VM is the reference. Are they equal? No. Right? But this is equal. So the first thing you want to make them equal is what? What's the difference? What's the difference? Feedback, yes. What kind of feedback? It has to be negative feedback. Has to be negative feedback. So the first bullet point is negative feedback. What's the second one? If you don't have an infinite open loop gain, for example, it's on like a 2, 3, 4, are you able to give that feedback super quickly? No, the gain is too small. It won't be able to provide that powerful feedback super quickly. Okay? So what are the 2 bullet points to answer that question? First, infinite open loop gain. Second, negative feedback. Perfect answer. I'll let you pass the interview. Conclusion, okay? Virtually short circuit. So they are virtually shorted because of the 2 bullet points. First, infinite AOL, open loop gain. Second, negative feedback. Okay, if you know this, you'll solve a lot of problems in the tutorial. Okay, for example, the first problem like this. This is homework. Where's tutorial? Over here. Like this, just asking you. This is a very simple problem, so I don't mind if the answers is being provided a little bit. Yes, okay. I believe this is negative 15 volts. Did it tell you it's negative 15 volts? Vx is 2 volts, and oh, they didn't tell you, which is okay. So this is 2 volts. Do you have a negative feedback? Yes. Are they equal? Yes. What is the voltage here? Right? What's the voltage here?
0.
Yeah. So 2 volts, 0 volts, what's the current here? Vx over R1, right? And given that the internal resistance of the op amp is huge, so there's no current flowing into the op amp. So it's going to go up and go that way. Okay? So what's the voltage at here? This is V out. This is the load. This is RL. This is the load. So what's the V out here? If the current goes that way. So it's causing a drop from left to right. Here's 0 volts. You got a current. So V out is Vx over R1, which is the current, times 25K. Am I missing anything? You get a current. The current is not flowing into the op amp. It's only going up. So it's the same current, Vx over R1 is the current flowing through it. Vx over R1 is the current, times 25K is the resistor, so you get a voltage drop, which is VO over 0. Is that correct? Anything I'm missing? So the current flows that way, right? And V out, if I'm talking about V out, I'm assuming this is plus, this is minus. It's compared to the ground. However, if the current flows that way, it becomes plus minus. So what should I do? Right? So that is V out. So which is over here, V out. That's ground. So what is the current? Just V out over 4K. So they are all calculated. That's how you do it, okay? What about this? You see it on the back? Okay. For the circuit shown there, determine the range of Vx so that op amp operates in the linear region. So linear region, which means it's not saturating like what I showed you, right? So the writer tells you it's a plus minus 15 volts. That's the range. That's the 2 power rails, 15 and minus 15. So your maximum output could be either 15 or minus 15. Cannot be beyond that. So you know the gain here. Did we derive the gain at all? RF, R1, V in, V out. You should be able to do this very quickly, okay? You should seal this in your mind. 0 volts. So what's happening is V in minus 0 over R1. That's a current. It's going to directly flow through RF as well. So that equals 0 minus VO over RF. Okay? And that becomes our VO over V in, which is the voltage gain, is minus RF over R1. Keep that in mind. Very important. For inverting.
How does the op amp do stuff with voltage if there's no current?
There's current. Oh, there's no. Yeah, that's another good question. I want to show that. So what's really happening is you are wondering, hey, if the op amp is not taking any current, why do we need it? Why do we still need it, right? That's a very good question. Why do we still need it? Let's see if we don't have it. Okay? Sadly, this guy is removed. Not there anymore. Okay? Gone. What's gonna happen? Are you amplifying anything? Why?
You just run into two resistors.
It's dropping by 2 times, depending on what these are. It's being dropped. If you have a load resistor, what's happening? It's a voltage divider. V out is what? V in times what? RL over what? R1 plus R, this is R1 plus RL. Are you amplifying anything? Are you able to amplify it? No, it's a voltage divider. It's dividing the voltage.
But if the op amp doesn't actually have any current input or output,
Yeah.
then why does it change the voltage?
Why is amplifying? That's another super good question. Look at this one. Why it is able to amplify it? For this configuration, why? Compared to this one, what is this one doing? Dividing, right? Voltage divider, right? You don't have an op-amp. Voltage divider. What is this one doing? It drops V in very quickly to 0 first, and then you can say it's dropping, but dropping to the negative way. But actually, the amplitude is actually increasing. So because the negative feedback and the infinite open loop gain, it forces this voltage to drop to the lowest voltage as soon as possible, amplitude-wise, okay? So is 0 voltage safe? Yes, right? Is negative 2000 voltage safe? No, right? So drop it to 0 is dropping the voltage to the minimum you can do. Dropping to negative 2000 is not, it's amplifying. Okay, make sense? Dropping to zeros, because 0 is nothing. 0 has no amplitude. It's nothing. It's not amplifying. All right. So for example, you have a voltage, negative voltage, being fed into an amplifier and put into a speaker. Okay. Negative 5 volts will give you a sound. Negative 5 volts, it's just the amplitude, will give you a sound. However, 0 volts will give you nothing. Make sense? So negative 5 is bigger than 0 amplitude-wise. Okay. So in this case, you reduce it to 0 very quickly, so it becomes nothing. And then because of the voltage drop, it's dropping the voltage negative to the negative way, but actually increasing amplitude. Eventually, for this configuration, since you have this op-amp over here holding the voltage, the two voltages are the same. Then your signal, here's the input, and it's being amplified. You are getting an amplified signal like this, even though the phase, it's called a phase shift. So look, because this one comes here, it becomes a sine wave again. It seems like this one, the output here is shifting the original signal's phase by 180 degrees. It doesn't matter. You can always invert it back by using another inverting amplifier. But the thing is, you are getting the amplitude amplified, which is the goal.
How much does it amplify?
You can define it by configuring the ratio of the two resistors. So usually 10 times to 20 times is ideal, but you don't want to do too much because the op-amps are not ideal. There's always a little, it's not ideal, which means they are not perfectly equal. So there will be a little offside, it's called DC offside, or just offside is being amplified. So eventually your signal, for example, your ideal case, right? Input, output, ideal, perfect, everyone is happy, not shifting. However, the real case is you got your input, your output is not going to swing around 0 anymore, it's going to swing around somewhere else. No. So what's the problem over here? The reason is there's a little DC noise is also being amplified. So if you amplify too much, your real signal will hit a limit because you have a 15 volts limit over here. It's shifting your signal probably to here. So if you still want to amplify by 20 times, it won't go up. It's going to saturate. It will be able to amplify the bottom part, but the top part won't be able to amplify. That's the problem. Because the DC is also being amplified because of noise. it's an unideal. It's not an ideal. You won't have an ideal op-amp in the real world at all, right? So
Also, on the other resistors, that and
R1. Okay, you have a question. Hey, why? So now we know why we need the op-amp, but you just want this point to be 0, right? Why don't we just ground it? I just need a 0. Why not just ground it? You lose your signal to where? To ground. So your signal got shorted to ground. It's gonna circle back to itself. It's getting shorted. So you want a ground, but you don't want a real ground. You want a virtual ground. That's why it's called a virtual ground. Why it's called a virtual ground? Because virtually shorted to ground, but it's not a real ground. It's not physically shorted to ground. You don't have a path to go to the physical ground. It's just providing a voltage very close to ground. However, they don't have a wire there. So it's not going back to the real physical 0 volts. Thank you for the good questions. I mean, I don't believe other sections will explain all these kind of details to you guys to this level, but we were not able to cover tutorial 6 problem, but I think understand this is very important. Help you to not get confused. Still have 4 minutes. I'm going to show you these how to solve these problems really quickly. Okay. So look at this circuit. So if it's asking you what is the range of Vx, possible range, you can always come back to the video. It's recorded. Okay. So how to figure out the input? There's the limit for the input, right? There's the limit for the input, because if the input is too big, definitely with a certain ratio here, it's going to saturate your output and saturate your output. It won't get a nice sound wave anymore, right? Here's our 2 rails. It won't receive a nice sound wave. It's going to be saturated. Okay, won't be able to swing nicely. So what you want to do is put V out as 15 volts and negative 15 volts, has 2 different cases. Plug it into the equation. Which equation? This equation. Make this one to be 15 or negative 15. Have 2 cases. Okay? Just assume it's hitting the limit now. All right? Since you know this ratio, you know the gain, because the resistor ratio here is given. Are you able to find out the range of V in? Yes. Let's calculate. So these are allowed V in to be used for the circuit by assuming the output is already hitting the limit. Okay? Here. Now it's not grounded. So it's Vx. What's the voltage here? You cannot just memorize it as like it's virtually shorted to ground. It's virtually shorted to the other terminal, not ground. Keep that in mind. So there are 2 concepts confusing people, like virtually grounded, virtually shorted. It's actually virtually shorted to this point. If this point is grounded, then this is virtually shorted ground. If this is not grounded, it's not virtually shorted to ground. So Vx over here is going to be Vx here as well. Okay? They're equal. These 2 are equal virtually. So if you know this is Vx, you know the current here. It's just a very simple KCL problem. Ignore this guy. Okay, the current flows that way. Very easy to calculate. So for the other problems, they are very simple, and there's only one thing that I need to go through on Friday. It's still midnight on Friday, so you are still fine. Which is a difference amplifier. I'm going to derive the voltage gain for this on Friday. Okay. All right, let's go.